Okay, oftentimes when you are solving exponential equations, you might have more than one term on the same side of the equation. And so what might happen is if you have something like 2 to the exponent of x plus 2 minus 2 to the exponent of x equals 24, the problem here is that we can't get 24 as the same base as 2. That's one of the problems. The other problem is because you have more than one term on the same side of the equal sign, you can't take the logarithm of both sides. We talked about this in the previous examples. You can only take the log of both sides if you have a single term on the left side and a single term on the right-hand side. So now what you need to think about is, hey, I have more than one term on the left side of the equation. I can't take the log of both sides. So what do? We need to use other techniques for solving exponential equations, such as your favorite F word, factoring, and the quadratic formula, okay? And so we need to look at different techniques of doing the question other than just taking the log of both sides, okay? So the problem that ends up resulting from this happening sometimes, this comes up sometimes, is that you might get something called an extraneous root. And so this is like inadmissible, not possible. It's the answer that doesn't make any sense. And so some algebraic methods of solving exponential equations lead to extraneous roots. Extraneous roots are solutions that are not valid to the original equation. It's sort of like if you're trying to solve for something and you end up getting x equal to -4. This is an extraneous root because you can't find the logarithm of -4, okay? So it's things like this, answers like this that end up being extraneous, that end up resulting from certain ways of solving problems. So here's another example of what I mean by an extraneous root. So for example, if you end up getting 2 to the exponent of x equals 1 plus or minus the square root of 5, this means you have two solutions. You have 1 plus the square root of 5, and you have 1 minus the square root of 5. Now this one, if I continue and I try to solve this, I can look at 1 plus root 5 as a single term because it just represents a number. If I take the logarithm of both sides, and I take the power law here, and I rearrange it and I try to solve for x, I get x is equal to approximately 2.08. This one is fine because I can actually look at the, I can actually do 2 to the exponent 2.08 and get a proper solution, okay? Now, the problem is here where I get 2 to the exponent of x equals 1 minus the square root of 5. If I write that as a decimal, I get 2 to the exponent of x equals approximately -1.23. Now, the problem here is if I try to solve for x and I use the change of base formula to do that, so if I go from a logarithmic form, exponential form to logarithmic form, I get log base 2 of -1.23 equals x. This part here I cannot solve. Okay, that statement doesn't make any sense. So whenever you have a power equal to a negative value, then you end up getting an extraneous root because that's something that you cannot find the solution of. So because this gives you a negative value, your power must always be a positive number, and so that means that the root is extraneous. So we're going to look at an example where this kind of problem would occur. Okay, so for example 3, it asks us to solve the following equation. So I have 3 to the exponent 2x minus 3 to the exponent of x equals 12. And so what you'll notice is that because there's more than one term on the left-hand side, in order to solve this, I can't just take the logarithm of both sides and try to evaluate it like I did the other questions. So instead, I need to either use factoring or one of the other methods that I know from before, okay? And so what I'm going to do is I'm actually going to try to write this in a different way. And first of all, I can recognize that 3 to the exponent 2x is the same thing as 3 to the exponent x squared. Okay, so this is the same thing as 3 to the exponent of x squared. Because the exponents are being multiplied here, I can write it as a power of a power using my exponent rules. And then if I continue to write the rest of the equation, what you'll notice is that I have one term squared minus another term equals 12. To make my work a little bit easier, I'm going to write 3 to the exponent of x using a different variable, and then I'm going to try to solve it based on that. So I'm going to let u equal 3 to the exponent of x. Now, if I rewrite this, replacing 3 to the exponent of x with u, what I get is u squared minus u equals 12. Now, this sort of looks like a quadratic equation, which is how I'm going to actually solve this. So I'm going to rewrite this so that it's equal to 0, and I'm going to try to actually solve this by using the quadratic formula or by factoring. So if I try to factor this, I need two numbers that multiply to -12 and add to -1. I think I did this right. Just want to make sure. So if I replace that here, I get u squared minus u equals 12. Yep, that seems right. And so if I actually try to factor this, my product is -12, my sum is -1. So the two numbers would be -4 and +3. That would equal 0. And so I have u minus 4 times u plus 3 equals 0, which means u has to equal 4 or u has to equal -3. Okay? Now at this point, because I'm actually trying to solve for x, I can replace u with 3 to the exponent of x. And so this would mean, therefore, 3 to the exponent of x is equal to 4, or 3 to the exponent of x equals -3. Okay? And so what you'll notice in this case is that this solution here is the one that's extraneous. I cannot actually solve this because you can't have a power equal to a negative number. So my only solution is 3 to the exponent of x equals 4. So this one's fine. But I'm not done the question yet because I actually need to solve for x. So I'm going to continue that up here. So if I try to solve 3 to the exponent of x equal to 4, I can't get the bases the same. Because now I have a single term on the left and a single term on the right, now I can take the log of both sides and then use the power law to bring it down. So I get x times the log of 3 equals the log of 4, and x is going to equal log of 4 over the log of 3. Okay, so there's an example with an extraneous root. I get a negative answer, and I can't have a power equal to a negative number, and so there's only one solution for the value of x. Okay, in the last example, we're going to look at a word problem, and it says, how long does it take for a $100 investment to double in value in an account that pays 6% per annum compounded monthly? Okay, so there's lots of information given in this question. First of all, I have a $100 investment, so that's my principal amount. It's going to double in value, so I want to know when the accumulated amount is double that, so $200. And it's going to be put in an account that pays 6% per annum compounded monthly. So monthly means 12 times a year. So I took my interest rate as a decimal and divided it by 12 to find the interest rate per compounding period. And then the number of payment periods, or number of times you get interest is going to be 12 times a year, depending on how many years that we actually invest for. So what I'm trying to solve for is the number of years that the money needs to be invested for so that it can double. Okay, so I'm going to plug in all the information that I know. 200 is my value for A, 100 is my value for P, 1 plus my interest rate per compounding period gives me 1.005, and my exponent is 12t, okay, 12 times each year. And so my goal is to try to solve for t, so the first thing I need to do is eliminate any coefficients that there are in front of my exponential term, so I'll divide both sides by 100, and I get 2 equals 1.005 to the exponent, 12t, and because I have an exponential term on one side and just a number on the other side, I can take the logarithm of both sides, and so I get log of 2 equals log of 1.005 to the exponent 12t, use the power law, bring it down, and I get log of 2 equals 12t times the log of 1.005, and now to isolate t, I need to divide both sides by 12 and log of 1.005. And I'll do that to both sides. And so on the right-hand side, I get t by itself. And on the left-hand side, this expression here is equal to about 11.6. Okay? So therefore, it will take about 11.6 years for the investment to double. Okay? That's it.